Hi everyone, this video is going to walk through a little bit of how to correctly use rates of change language and how it relates to our functions. I know there's been other videos that talk about this, but you never know if seeing it in a slightly different way might help. And instead of just having some written notes, I'm doing a video so that I can sort of show you in a Desmos calculator what we mean by rates of change and what's happening. Because it's really the sort of key thing going through my mind when I think about how the function's rate of change is changing is I imagine a little tangent line attached to the graph, or a piece of spaghetti stuck to the graph that shows the slope at a given point along the function. And I think about how is that slope changing as I increase my input values. And so I'm assuming that most of us are pretty good with constant rates of change. Therefore, we have lines. And when I say that, as the input increases, the rate of change stays the same or it's constant. So I'm not going to focus so much on that. Instead, I'm going to be looking at the increasing at an increasing rate, increasing at a decreasing rate of change, and then the decreasing at an increasing rate and decreasing at a increasing rate, whichever one I didn't use. So to see some of the written stuff, I have a post for that, but this video is just to sort of supplement and add to. So what you see going on here is I have this blue function, and you'll notice that I've made my own little mini piece of spaghetti that I've slapped onto my graph. This is actually a tangent line. It touches the graph at one point, and the neat thing about tangent lines, as you'll learn more in calculus, is those illustrate basically what we call the instantaneous rate of change, the slope at that given point. And so right here on this particular graph, right here at, and I'm gonna lost my drawing tablets, but right here at 0, this black line represents the slope at that point, and so the slope at that given point is about 1.5. And what I did here is if we sort of move our slider along, you'll notice 1 unit over. So our input value has increased by 1, but my slope has decreased. So notice now my slope's only 0.3. 0.3 is less than 1.5. And if I increase my input again, my slope went down a little more. And then if I increase my input again, my slope went down a little more. So notice each time that rate of change at the point is getting a little smaller and smaller and smaller. So what we describe here then is, yes, my function is generally going up. My rates of change are positive. My output value is increasing as my input values are increasing. But I can say as x increases, my rate of change in y is getting smaller and smaller and smaller. Each subsequent rate of change, as I move over, is less than the previous one. Now, when we talk about what the appearance of the graph looks like, we often refer to this graph as concave down. And a decreasing rate should result in a concave down graph, and that normally has sort of this curve that's sort of some people think of it as like opening downward. Now, if we look at another way a graph might increase, I have this second graph. So notice this green curve right here, and if I sort of start putting in a slope line, well, right here the slope is 0. But if I go 1 more over, now my slope is 1/2. So we're increasing a little more than we were at the previously we weren't increasing at all. But then if I increase my input again, now my slope's at 1. If I increase my input again, now my slope's at 1.5. And while it's off the graph, if I increase my input again, now my slope is 2. So notice all of those rates of change as x increases, my rate of change of y increases. So we would describe this as this function is increasing at an increasing rate of change. And notice this curve now, instead of sort of curving downwards, this is curving upwards. And so we refer to this as concave up. Usually people feel pretty comfortable describing rates of change when the functions are increasing. We run into some confusions and complications when we start looking at decreasing functions. So I have a third graph with tangent lines where we have a decreasing function. This is just a cubic function. It's decreasing. And you'll notice, so this initial, so there's sort of two pieces to the graph. Sort of 4 is what we would call a point of inflection. And this initial curve, it's tempting to say, well, the rate of change is decreasing because the slope of this tangent line, the tangent line is getting less steep. So that would make sense that the slope is decreasing. But we're talking about rates of change that are negative. And this is where it gets a little weird. So when we talk about negative values, at 0, we have a slope of negative 3.2. And then at 1, we now have a rate of change of negative 1.8. And at 2, we have a rate of change of negative 0.8. And if you compare those numbers, and then the next one is negative 0.2. Negative 0.2 is a larger value than negative 1.8. Think about it as if you were in debt. If you were in debt, would you rather owe $1.8 million or $0.2 million? I'd rather owe the $0.2 million. So it's getting less negative, which means the values are actually getting bigger, which means it's actually decreasing at the function is, the output values are decreasing at an increasing rate. So we would say in our sort of rate of change sentence, as our x values increase, the rate of change of y is increasing. It's an increasing rate of change. But our function is decreasing. So I often go, the values of y are decreasing at an increasing rate of change is usually how I like to word it. I like to say in general whether the function's going up or going down. Now, if we then go after 4, and 4 is that point of inflection I talked about. So points of inflection, we actually have rates of change of 0. But then when I go after 4, you'll notice, okay, now we have that negative 0.2 rate of change. And you might be thinking, well, the line's getting steeper, so my rates must be getting bigger, but we're dealing with negatives again. So remember, a rate of change of negative 3.2 is actually a smaller rate because it's more negative than a rate of change of negative 0.8. And so our rates of change are actually getting to be smaller values because they're more negative. So this is decreasing at a decreasing rate of change. And so we would describe this as x increases, that rate of change is decreasing at a decreasing rate. That y value, that output values are decreasing at a decreasing rate. And this matches sort of the concavity talk we were having on the previous one. Notice where we have that decreasing rate, that curve is curved downwards. So we have a concave down graph. Concave down graphs are associated with decreasing rates of change. Just as our concave up curve over here, this curve is sort of open, it's curving up, increasing rates of change. Hopefully this helps a little. So I will have the video along with the links to these graphs if you want to play around with the sliders and sort of take a look. This is just a fancy math notation for basically saying the slope at that point. You'll learn more about it in calculus. Hopefully this helped clarify some things. If not, feel free to reach out and we can try a different way.